Hello everybody, welcome to this second video lecture of week 11, which is also the last video lecture of our course, at least in the sense of new content. So our topic for this last one is quotient groups. And really the goal is just to try to understand what a quotient group is, to observe that we are familiar with the concept already, at least in terms of some examples, and to understand the connection to normal subgroups. So with that in mind, I want to first of all recall the concept of the image of a group homomorphism, which we talked about last week. So let's suppose we have a homomorphism from a group G to a group H with kernel N. And we know that N is a subgroup, in fact, a normal subgroup of the group G. And we saw in week 10 that the distinct elements of the image of phi over in H correspond exactly to the distinct left cosets or right cosets of N in G. What I mean by that basically is the two elements of G have the same image in H if and only if they belong to the same coset of the kernel of phi in G. The kernel of phi is a normal subgroup of G. That means that its left cosets and its right cosets are the same thing, so we can just talk about cosets. We don't have to distinguish between left cosets and right cosets. Okay, so two elements of G have the same image under phi if and only if they belong to the same coset of N in G. And that means they have different images if and only if they belong to different cosets of the kernel. So the distinct elements of the image of G over in H correspond exactly to the distinct cosets of N in G. So we have this correspondence between elements of the image of phi and cosets of the kernel in G. And using that correspondence, we can just move over and back between cosets of N and G on one hand and elements of the image of phi on the other. The image of phi is a group. It's a subgroup of H, and the mechanics of group homomorphisms tells us that it is a subgroup of H, not just a subset. Every element of that group, the image of phi, corresponds to a coset of N and G. So through that correspondence, we can actually get a way of multiplying together cosets of N and G. We can take a pair of cosets of N and G. Each of them maps over to an element of the image of phi. By phi, they can be combined over in H, and that element corresponds to something, which is another coset of N in G. And because of the fact that what we're dealing with is a group homomorphism, what this is saying is, if we take two cosets of N and G, take an element X of one of them, an element Y of the other one, look at their images under phi over in H, compose them in H, we get to the same point as we would if we multiplied X and Y together in G using the group operation, taking the element X composed with Y in G, and then apply phi to that. So essentially what we're saying is, through this correspondence of the elements of the image of phi with the cosets of N and G, we actually essentially have a way of multiplying cosets of N and G together to get new cosets of N and G. And what we actually end up with is a group structure on the set of cosets of N and G itself, which is exactly sort of the mirrored copy of the image of phi over in H. So basically, just to recap, we have this correspondence between cosets of N and G and elements of the image of phi. The image of phi is a subgroup. Its elements can be composed together within H with a group structure. That group structure translates back via the correspondence to a group structure on the set of cosets of N and G itself. This group structure is basically something called the quotient group of G modulo N, which we're going to study in this section. And it arises whenever you have a normal subgroup of a group. So I want to mention one other thing in connection with this, which kind of takes us back to Lagrange's theorem. So when we were studying Lagrange's theorem, we saw that if you have a finite group G and a subgroup of G, then the order of the subgroup would be a divisor of the order of the group itself. And you could sort of ask, supposing you have a group G of order 24 and a subgroup of order 6, then, okay, you've got the subgroup of order 6, and you divide 6 into 24, you get 4. And you might kind of wonder, well, okay, is this group G somehow the product of this subgroup of order 6 in some way, and some other subgroup, some other group that would have order 4? Okay, there's some way that the group sort of splits up as a product of this part that has order 6 and something else that has order 4. The answer to that in general is no. There just isn't. There isn't a way of sort of dividing one group by a subgroup and getting another group as the result. But when the subgroup that you start with is normal in the big group, there is a way of producing from that setup another group whose order is like the complementary factor to the order of the subgroup. So if you have a subgroup of order 6 and a group of order 24 and it's normal, then somewhere in the mix is a group of order 4 that somehow is a sort of a companion to this subgroup of order 6. The group of order 4 is not itself a subgroup of the original group, but it's what they call a quotient group. It's the quotient group of the group G modulo this normal subgroup. So we can't divide one group by another. We can't sort of talk about really factors or division or anything like that. But the language of quotient group does sort of suggest that idea. And when we have a subgroup which is normal, we do have this possibility to create from a group G of some given order and a subgroup, a normal subgroup of another order, a third group whose order is the complementary factor to the order of the subgroup in the group. So basically, if the group has order, like I said, let's say the group has order 50 and the subgroup has order 10, and it's normal, then somewhere in the picture is this group of order 5, which is the quotient of the entire group by the normal subgroup. This phenomenon only arises when the group is normal, when the subgroup is normal, which of course happens in the case where it's the kernel of a group homomorphism. But it can also be kind of envisaged and realized without a homomorphism necessarily being in the picture. But I think this idea of thinking about the image of a group homomorphism, which is essentially a copy of the quotient group of the domain G modulo the kernel N, is something that's actually useful to have in your mind when you're thinking about this phenomenon. So what we're going to do in the next slide is consider the case where we just have a normal subgroup of a group, not necessarily in the context of a group homomorphism, and figure out how to define the quotient group of the group modulo the normal subgroup. Okay, so quotient groups. So a quotient group, when you have a homomorphism from a group G to a group H, you've got this normal subgroup, which is the kernel. The quotient group of G modulo the kernel is essentially a copy of the image, where the elements correspond to cosets of the normal subgroup in the entire domain group. When you don't have a homomorphism in mind, but you just have a group G and a normal subgroup N, this is sort of how it goes. Suppose we have a normal subgroup of a group G. So remember what normal means. It means that the left and right cosets generated by or determined by any element are the same set. It also means that N contains all the conjugates in G of each of its elements. So we're going to try to define a multiplication or a binary operation on the set of cosets of N and G, which is often written this way, like a fraction, G over N, read as G modulo N, the set of cosets of N and G. And the way that the multiplication operates is if we take a pair of cosets, then to define what we mean by their product, we take a pair of representatives of the two cosets, compose them using the group operation in G itself, and then take the coset that is represented to which that product belongs. So that's what's actually written in this equation here, which is written in blue, although it might not be so clear. The thing to focus on is we're taking a pair of cosets. They look like this. There'll be xn and yn for some x and some y. Important to note that the coset xn could also be written potentially as like x dash n, where x dash is another element of it. It doesn't necessarily depend on this particular element x. So we take a particular pair of cosets, write the first one as xn, so you're sort of choosing a representative x of that coset. Write the second one as yn, so you're choosing a representative y of that. We're writing them as left cosets. It doesn't matter if we write them as left or right cosets because we're in a situation with a normal subgroup. So the left and right cosets coincide. We define what we mean by the product of the coset xn and the coset yn to be the coset that is represented by the element xy. This is xy is the product of the group elements x and y in G. Okay, that's a way of sort of determining what we would mean by multiplying a pair of cosets. We take a representative of each, combine those in G, take the coset to which that element belongs. There is an issue here, because when you look at this definition, you might ask yourself, okay, well, that's fine. I have a coset, I pick an element x of it. I have another coset, I pick an element y of it. I compose x and y up in the group G. I take the coset to which that product belongs. In order for this thing to make sense as a definition of multiplication of cosets, you have to know that the coset represented by the xy that you end up with here does not depend on the particular choice that you make of a representative x of n, of xn, and a representative y of your second coset yn. So the first bullet point here confirms that this operation is in fact well defined, but that depends on the fact that the subgroup n is normal in the group G. So suppose we take a particular coset of n, and we have two choices of a representative. We could choose x or we could choose x1. So xn is equal to x1n. That certainly happens. If we have there'd be multiple elements that determine the same coset, the same left coset. And suppose also that the second coset we pick, it could be written as yn, but could also be written as y1n. So y1 and y are potentially different elements of G that both determine the same coset of n. So if that happens, then okay, you're given these two cosets. You write them down as xn and yn. You follow this instruction, you get the coset determined by xy. Somebody else writes down their two cosets, the same two cosets, to represent them as x1n and y1n. And they say, okay, I follow this instruction. I multiply x1 and y1 in G. I get x1, y1. I take the coset that represents. You need to know if this multiplication makes sense, that you're going to land in the same coset. So you need to know if x and x1 represent the same coset, and y and y1 represent the same coset of n in G, that the product xy and the product x1, y1 represent the same coset in G. So that's what the statement of well-defined is about, that this is a well-defined multiplication instruction for multiplying cosets, that it's robust, that it doesn't depend, that where you end up from a pair of cosets does not depend on which representatives you choose from each coset. Okay, so what we need to know in this situation is that xy and x1, y1 are in the same coset of n in G. Okay, if xy and x1, y1 are in the same coset, that means that xy n is equal to x1, y1 n dash, where n and n dash are elements of n. So in particular, it means that there's an element n of n for which xyn is equal to x1, y1 n dash for some n dash in n. And that means that the inverse of xy composed with the element x1, y1 must be in n, okay, in order for these two elements to determine the same coset. Okay, so let's look at this element. The inverse of xy is y inverse x inverse. So this is y inverse x1, y1. X and x1 are in the same coset of n. That means that x inverse x1 is an element of n. So this expression we can split it up into two parts and write it as y inverse x1 times y1, knowing that x inverse x1 is an element of n. That y inverse x1 y1 we can write as y inverse x1 y multiplied by y inverse y1. So here we've introduced an extra copy of y and y inverse, which overall is just introducing an identity element, so it doesn't do anything. But putting the y inverse x1 y part in front, we know that x inverse x1 belongs to n. We know that n is a normal subgroup of G. So if we have an element of it and we take a conjugate in G of that element, so y inverse x1 y is a conjugate of x inverse x1, so it belongs to n. Second part, y inverse y1 belongs to n because we know that y and y1 belong to the same coset of n. So this element y inverse y1 belongs to n for that reason. So what we've shown overall is that xy inverse x1, y1 is a product of two elements of n, so it belongs to n. And here we've used the entire power of the fact that n is a normal subgroup, that it's closed not only under its own multiplication, but under taking conjugates of its elements as well, which is what we've used here. So our conclusion is that as long as x and x1 represent the same coset of n, and y and y1 represent the same coset of n, then the elements xy and x1, y1 represent the same coset of n as well, so that this equation up here does define a reliable multiplication of cosets that doesn't give you different answers if you choose different representatives. That fact is dependent upon the fact that n is a normal subgroup of G, and not just any old subgroup, in which case it wouldn't be true. So we have this multiplication operation on cosets. It's associative because it comes from this associative operation on G. It has the element n itself as an identity element, And a given coset xn, represented by x, has the coset represented by x inverse as its inverse. So it actually defines a group structure on the set of cosets of n and g, where g is a normal subgroup, where n is a normal subgroup of g, and that thing is called the quotient group g modulo n. Okay, its number of elements, if we're in a finite setting, would be the number of elements of g divided by the number of elements of n, or the index of n in g. Okay, it's not a subgroup of g, it's a group whose elements are the distinct cosets of a normal subgroup in G. So this is quite a weighty concept conceptually, and it's one that is not entirely unfamiliar to us. So I'd just like to give a couple of examples, one of which is one that we've known about for quite a while, although not in the language of group theory possibly. So the subgroup 5z of the additive group of integers is a group consisting of all the multiples of 5, 0, 5, 10, -5, -10, and so on. And we can confirm easily that that is a subgroup of the integers under addition. The cosets of the subgroup are the congruence classes of integers modulo 5. There's 5z itself, which we can write as 0 bar. There's the things that we get by adding 1 to everything in 5z, which is all the integers that have remainder 1 upon division by 5. That's the congruence class of 1 modulo 5, which we'll call 1 bar. There's the coset determined by 2, which consists of everything that's 2 more than a multiple of 5. There's 3 bar and 4 bar. These are the congruence classes of integers modulo 5. And we know that the quotient group z mod 5z is the additive group of integers modulo 5. Its elements are these 5 congruence classes. And what you do if you want to add a pair of them is you just choose a representative from each, add them together in the integers, and drop down to the congruence class that you now are in. So if you want to add the element 2 bar and the element 4 bar here, what you would do would be take a representative of the element 2 bar, like 2, take a representative of the element 4 bar, like 4, add those in Z, get 6, take the congruence class to which 6 belongs, which is the one represented by 1, which we're calling 1 bar. So that's what you get if you do 2 plus 4, but you can take any representative of 2 bar and any representative of 4 bar and do the same thing, although the most obvious ones to take are 2 and 4, you don't have to. As a representative of the congruence class of 2, you could take 17, which is 2 more than a multiple of 5. As a representative of the congruence class of 4 modulo z, you could take 19, which is 4 plus a multiple of 5. If you add 17 and 19, instead of adding 2 and 4, you get 36, which again is 1 more than a multiple of 5. So you again land in the same congruence class. And the point is the addition of these classes is well defined, because what you get by choosing a representative of 2 classes, adding them, and then dropping back down to the class that you've landed in, doesn't depend on the particular choice of representatives that you've picked. And that's exactly the same as with what we talked about in the previous slide in the general context. In this case, it comes for free that 5z is a normal subgroup of z, because z is an abelian group, so all subgroups are normal, so you don't have to dwell on the fact of the normality, but it is actually there behind the scenes. Another example, the subgroup n, consisting of the identity element and the rotation through 180 of the dihedral group of symmetries of the square, is normal. This R should be an ordinary R, not a real numbers R, is a normal subgroup. It has 4 cosets, of course, because the index of n in D8 is 4. It's 8 over 2. 2 is the order of the subgroup. The group table, the 4 subgroups, the 4 cosets of n in D8 are represented by the element's identity, rotation through 90 degrees, and 2 of the reflections, one in a bisector of 2 opposite sides and another diagonal. And so if we call SL and SM are 2 reflections, we can write out the group table. And here it is. The subgroup itself, N, is going to act as an identity element. Okay, to compose, for example, SL with rotation through 90. Take a representative of SL, take a representative rotation through 90, compose them, look at the coset that you've landed in, and it'll be the one represented by the reflection, SM. So the details of this example are in the lecture notes, but the key point is we're just taking a normal subgroup. This normal subgroup, in fact, is the center of D8, looking at the 4 distinct cosets of that subgroup in D8, choose some representatives for them, and you can figure out the multiplication table. And what you do at each step in the table is just compose the 2 reflections that the two representatives of the 2 cosets that you have. So if you're doing SLN composed with R90, you compose SL with R90 in D8, calculate that composition there, look at which of these 4 cosets that you're in when you do that, and answer to that is the entry that goes into that particular part of the table. So it's a subgroup of order, sorry, it's not a subgroup, it's a group of order 4. It's a quotient group of D8, modulo this normal subgroup, which is its center. And it's a companion somehow, a group of order 4 that's sort of a companion to this subgroup of order 2 of D8. And the 2 and the 4 together, when you multiply them, make 8. The fact that the subgroup of order 4 exists is due to the fact that what we are dealing with is a normal subgroup of D8. If you took a non-normal subgroup of order 2 of D8, such as one generated by one of the reflections, there would be no corresponding version of this quotient group. Okay, so that's the concept of a quotient group. And I guess it's kind of it's sort of the last major idea that we have in the course. It takes a bit of time to get used to, I think. So when you're thinking about it, my advice would be think about homomorphisms and their images. Think about these examples of addition of integers modulo n. And think about how all of those are examples of this phenomenon where you have a normal subgroup in a group and you can define a group structure on the set of its cosets. And the key point is that argument that we had in the last slide, which is basically when you are in this situation with a normal subgroup, you can define the multiplication of cosets in a way that operates consistently and independently of particular choices of coset representatives when you're doing the multiplication. Okay, that's it, essentially. Here is our final weekly challenge, challenge 2 for week 11. Again, it's about normal subgroups rather than about quotient groups. The challenge is, as we know, the symmetric group Sn is a group of all permutations of the set of n elements 1 to n. The challenge is to show that the only normal subgroup of Sn that contains the element 1, 2, the transposition that swaps 1 and 2 and leaves all the other n minus 2 elements alone. Any normal subgroup that contains that element must be the full group Sn itself. And it's a tricky challenge, I think. It sort of relies on using your full understanding of the concept of a normal subgroup, as well as knowledge of conjugacy in symmetric groups. So my advice would be to bear in mind the fact that if you have a normal subgroup that contains any particular element, it must also contain all the conjugates of that element in Sn. And ask yourself, what are the conjugates of this element? We know the answer to that one from our work earlier in the course on conjugacy classes in symmetric groups. Okay, that's it for this one. Thank you very much, everybody, and see you later in the